helps guideline the non-destructive testing or examination. Okay, so this is a recommended practice. It's not a code. Now it can be in compliance or used as a guideline to adhere to a certain code. All right, but as of right now, this is just a recommended practice of how they prefer you do this. Welding codes and standards, for sure. So let's give you an example of what's the difference between the two. Over here on the side is AWS D11. It's a structural welding code. Let's look at API 1104. This is API standard 1104. So 1104 is for pipelines, right? And related facilities. Structural steel over here is a code, and that one is a standard. And then naturally, we come back, we look at this recommended practice here. I know, it's rather confusing. But they all have their special place in everything that we do. All right, and under standards, we read what the definition was. Second paragraph said some standards are considered to be mandatory. This means the information is an absolute requirement. This is the case for 1104, right? This standard is a mandatory standard, even though it's not considered to be a code. All right, moving on, I'm on page 5-7. I'm going to talk the left-hand column, top paragraph, 3 sentences down. It starts out, non-mandatory standards include words such as should and could in place of shall and will. You might see that on a test question. What's the difference between the two, or what are they referencing at that point? I want you to read the next paragraph about recommended practices, particularly S&T TC1A from the American Society of Non-Destructive Testing. And then the following one talks about the ANSI standards and how they're developed and according to rules set by ANSI, but ANSI doesn't actually write them. Okay? 1, 2, 3, fourth paragraph down talks about standard of welding pipelines, the API 1104. One below that is the American Society of Testing Materials, produces many volumes of specifications, so forth. And part of the reason why there is so many of these is because most of you know at this point that from welding and everything else we've learned is that when you change the variables, it can do a lot of different things, right? So we can have the same amount of steel that's going to act differently on structural welding code, D11, and then that same exact steel over there on bridge welding, maybe if it's in a high environment or it's got a corrosive environment, it's going to act completely different. Any of you that's taking materials engineering, you're going to say, well, yeah, of course, we learned that stuff, or it was always frustrating at that point. But this is the reason why there's so many different specs, and then there's some of them are codes which are standardized, and then there's recommended practices. And a lot of times the practices will tell you, they'll have you refer back to an actual code as well. Okay? So in ASME is a good example. You're always going to be referring to back and forth usually between section 9, which is welder qualification, and then you're actually going to go to the actual applicable code at the same time as well. Okay? Let's talk about specification. We can read the definition here. Detailed description of the parts of the whole. Statement or an enumeration of particulars as to actual required size, quality, performance, terms, and etc. Just got the main highlighted piece here. Another specification that might be there is 85.01, which is the filler metal procurement guidelines the American Welding Society writes. Right here. So you might be using this in conjunction as well as your D11 welding code, or any of them really. Almost all of your other codes are going to apply or reference your filler metal specification. Even ASME's is very similar to AWS. I actually think they adopt the AWS filler metal standards. Okay. Here's specifications, individual ones. All right. Let's get into control materials. This is extremely important, especially accountability and traceability, okay? So when we talked in chapter 3 about producing an ingot, blooms, billets, or slabs, right? And so then from that point it can be drawn out into steel, drawn over mantle type tubing, seamless pipe, whatever the application is that we're going to be using at that point. But it's got to have a heat number, a lot number, to be able to trace it back to when was it produced, what was the chemical makeup of it, what was the minimum yield strength to test, what was the lab report that it come back on, right? So for every time you pour a batch, you're usually going to have, they're going to pour a separate batch or a separate piece of steel at the same time they pour everything else. And they're going to test this material. They're going to break into 3, 4, maybe even 50 different test samples. And they're going to use it and test it with multiple things all at one time. Okay? And that's called your batch, your lot number, your heat number. These are all things that can trace it back to when it was produced, to what facility, what's the chemical makeup, what's the stress strength, and what's the engineering standards that it's going to be used in as well, right? This is all starting on the material test report, okay? And we're going to go through this here in a second and break that down. But the control materials can be something as simple as this needs to be just like 7018 welding rod, right? Control materials is exactly like 7018 welding rod. Who's documented, when was this box opened? If you're in Portland and it's raining, this box needs to be open, it needs to go in a rod oven almost immediately. If it's not, then it's a bad filler metal. It can get rejected at that point if it hasn't been confined in the space. So we've talked a lot about just the metal at this point, but the filler metals especially, 718 welding rods, that's a huge part of control materials as well. What's the manufacturer of it? What's the size specification? So if the welding procedure is for 1/8 inch, you cannot go any larger than that, okay? Because number one, it requires more amperage and that therefore requires more heat input and everything else, which we get into next when we start talking about metal properties and everything else, okay? But as for right now, we're going to be control materials. I want you to start thinking about how these things change and how important they are, especially for any government contract, anything that's going to be, especially a really wild engineering spec, say a bridge or something or a building. We want to make sure that we have a good amount of traceability. Now, for a light fabrication piece or somebody's decorative artwork, are we going to be concerned about it? No. At that point, we're really not. More than likely, we are not going to care at that point at all. Okay? So, that's important because you need to know this. When you go to buy that steel or spec it, you need to know exactly what material you're looking for, and you also need to make sure to ask the provider, sorry, I put something on my eye here. You need to require a material test report, and not just an MTR, a material test report, but you also need to make sure that that MTR actually matches the heat number on it, right? Almost all of them have it sprayed, painted on the side, or it's stamped on the side, or it comes with a barcode, things like that. This is the starting point. So this is the batch. Here's a good example. So right here it tells you Trent Tube was the manufacturer of this steel, okay? Bigger, somebody else produced this steel. And if you look through here, it's the report of the test. So here's your heat number. Here it's telling you, oh, this is lot number 671249. Here's how much carbon is in it, magnesium, potassium, silicon, nickel, chromium, molybdenum. It's telling you the chemical makeup that came back out of that, okay? And that's really important to understand and know. And then if you look further down here, that was just the chemical analysis. Now we're looking at mechanical and UDE tests. So did it come out with visual inspection? Was the grain pattern correct? And then down here, let's look at the tensile strength, and here's the minimum yield strength of 51,000. If the tensile strength's at 98,000, okay? These are the types of things that we're getting there, and it's going to tell you all of that stuff right here, okay? The date of manufacture, the date of the pour, where it come from, where it originated from, and this is going to be global, right? This isn't always just here within the local U.S. This could possibly be global. Your material control system, try to make it as least complex as you can. It's the best thing I can tell you. Because the more complex it is, the harder it is to follow it, okay? I'll give you an example. You know, we occasionally will buy some tube in here. We make sure to get the MTR report. So if we're going to take a test, qualification or certification test on it, I have to keep track of that. We as a facility do. So one of ours, if you go out and you look at our pipe, it may have a yellow paint strip down it. And so what we're going to do on that MTR is we're going to pull it in. It's 2-inch pipe, Schedule 80. And we're going to say yellow paint stripe received on this date by this person. This is how many feet of material we got out of that. We make sure that the heat number matches, the lot number matches, and everything else. And then as soon as that yellow one is produced, then I'm going to come in and document over top of it the last piece was used in the yellow stamp or the yellow paint marker, and the given date at that point. Then the next piece that's going to come in might be a blue piece of paint, right? I'm going to put a paint stripe down, and that's my traceability. That's some simple systems, okay? So when we talk about color coding, that's what I was just describing, was color coding. Some smaller shops might be segregation. So you might have 4 different iron racks, right? And only certain ones will go to certain iron racks to come back and so forth. You can do alphanumeric, barcoding, tagging, stamping, however you'd like to do it. But again, make sure that it's complex. So for example, tagging or stamping, if you're going to stamp it, you have to remember that you've kind of changed a little bit of the metallurgical fact now. That might be a notch toughness issue, okay? If you cut that corner off and it's got a stamp or a tag on it, then you need to make sure that you put that on the other corner of that piece of plate, all right? Make sure that you're keeping the positive material identification. It's finding its way into the industry. I'm on page -513, left-hand column, halfway down. It says a successful system for material control has several attributes. First, it should be as simple as possible. If it's too complex, it's hard to follow. So the next page and a half talks about all these methods. Work your way through them. Okay. Now we're going to move on into the alloy identification systems. Industry associations, SAEA, ISI, so Society of Automotive Engineers, the American Iron and Steel Institute, all these other ones as well, okay? The American Society of Testing Materials, right here. I know Book of Standards. So these are going to tell you the alloy identification, the material properties, the mechanical properties. Particularly in this one, it's volume 3, so it's metals and mechanical testing of low temperature tests, okay? And why does that matter? We're going to talk in chapter 6 how metal reacts differently when it's cold versus hot. Okay, directly proportional in steel and iron, because the hotter it is, as you can imagine, we bend things once we get them hot, but when they're cold, they can be somewhat brittle, okay? So here we talked a little bit about standard 514. Standard spec for high yield strength, quenched and tempered alloy steel. Might be HSLA, high strength, low alloy, correct? So forth. This is on page -514. Feel free to read through this and get yourself familiar with the primary UNS numbers. Okay. We've talked a little bit about this in metals prep at this point as well. I'm not going to hit too much on it. Remember to know, come ask questions if you need them. Particularly, I want you to look at the scope one of this. The scope tells you the statement explains exactly what is to be described by the specification. That is, it defines the limits of the spec's coverage. Okay? So in this case, it may tell you aspect is particular to this process or this material, or only 2-inch pipe, or only round steel for this amount of material. Okay? If it changes, then you may have to go to a different section. AWS 85.1, the spec for welding electrodes. That's on page 5-16. Feel free to read through it. We talk a little bit more about this with Sharpie V-notch and everything else later on. Here's mainly where I wanted to get to, was the procedure qualification. There's a lot of stuff in here, so we're on page 5-16, right-hand column halfway down. Okay, so now we're starting to talk about welding procedure specification versus procedure qualification record versus WPQR, welder performance qualification record. All right? So the procedure qualification determines the capability of the base metal, the filler metal, the process, and the techniques. Okay? So, I kind of need to do a little bit better job of this, in my opinion. So I'm going to read from the book here. Left hand or right hand column, 3/4 of the way down. That paragraph starts out, most codes place the burden of responsibility for qualification on the fabricator or the contractor. Okay? Therefore, welding qualifications are statements by the company verifying that the welding procedures and personnel have been tested in accordance with the proper codes and specifications and found to be acceptable. So you can have and we'll talk here in a little bit about pre-qualified procedures, but again, you can be qualified versus certified. Okay? So, probably the three best ways I'm going to explain this, right? And they do a bad job of saying this. Is the first thing you have to have is you have to have a specification. So the welding procedure specification is going to tell you the overall scope, so to say. So that's going to say it's going to be a pre-qualified procedure. It's going to be D11. Say it's our unlimited thickness 1-inch groove plate. Okay. So that specification is going to give us the outlines and the guidelines of what we can do. So the best way that you would need to start with any of this is you'd have to say, here's what I want to join together. I want to join these two pieces of 1-inch steel together. I need one of them to be flat, I need the other one to be beveled, and I'm going to say a 30-degree bevel, and I want this much of an opening, and I want to weld them with 70-18 all the way, and I'm going to see if that if that sticks together. So, in order to write a WPS, it's kind of like who came first, the chicken or the egg, right? We know that we want to get the chicken out of the egg, but in order, which one do we have to do first? So, the procedure qualification is just that. We're going to decide what we're welding, the 1-inch straight, 30-degree bevel, A36 steel, with a backing strip, 70-18. That's what we're going to do. We're going to do it in a vertical and an overhead position. We're going to use 1/8-inch electrode. We're going to watch the heat input. We're going to time it. We're going to measure everything. How much amperage is going into it, how much voltage is going into it, how much heat input is into it. We're going to do that off of a formula because we're going to time you. When you strike an arc, we hit a stopwatch. You're going to weld for 28 seconds. We stop it, and then we're physically going to measure how far you welded, and then put that equation in there versus 60 seconds per minute. Then we can transfer that over to amperage, voltage, our heat input, and everything else. Okay? So we do all of that, right? And then we weld it. We can either preheat it, and a lot of times you'll do maybe one preheated at 250 degrees, one as welded, or 70 degrees plain temperature, okay? And then you're going to see if the difference between the two works out as we go to test it. So we've got two of them welded, exact same thing, one at an elevated temperature, one at a base metal temperature. If everything matches the spec, so we follow the code guidelines of, say, AWS D11, the undercuts within visual acceptance, the weld profile is correct, everything else meets spec, it's a good weld. Then we're going to cut it up into the pieces that we're going to try, and we're going to test it. Now we're going to be mechanically testing it. Okay? So I'm going to skip forward a little bit ahead. So we're welding this one here. But now, so here's a fill weld one, but it gives us pure guidelines of where we need to test and where we don't need to test. So I'm going to come back a little bit. My lights went out on me. Give me a second, let me find some paperwork. And we'll continue back.